Hi everyone, today we are going to present our work, RMP, a random mask pre-train framework for motion prediction. The work comes from KTH, Scania, and Mines Paris, PSL. If you are interested, please check our code on GitHub. While learning-based motion prediction has become increasingly popular in recent research, the exploration of pre-trained and self-supervised learning within this field remains relatively limited. The techniques of random masking has demonstrated its effectiveness in various fields, such as NLP and computer vision. It has proven to be particularly powerful regarding training speed with large datasets and shows the good performance in transfer learning. Take masked autoencoder as an example. Random masking involves concealing a portion of data and then tasking the neural network with predicting the hidden elements, thereby creating a non-trivial and beneficial self-supervisory task. Inspired by Sync Transformer, the motion prediction task is also linked to mask on the fusion time sequential data of road user, as shown in the grids, with time and agents forming the two axes. In this format, the motion prediction becomes a unique task, wherein future states are masked in blue, and we can apply random mask easily as shown here. In reality, the masking effect looks like this. Then it leads us to a natural question. Could random masking pre-train be effectively applied to general motion tasks as well? We introduce a simple yet potent framework for random mask pre-train for motion tasks. These tasks include motion prediction and occlusion handling. Our method selectively masks motion patches, allowing the random mask to capture spatial and social correlations among all agents in a given scenario. The framework has two phases. In the first pre-train phase, all agents' information, including the history and future time, are concatenated together. Next, a random mask is applied. Then, given incomplete information about agent's position with time in gray, where some positions are randomly masked in blue, the network trains to fill in the blue missing positions. In the fine-tune phases, there are three tasks that correspond to three special masking cases. Once trained, the pre-trained encoder is used for different tasks. In this paper, we demonstrate its adaptability by incorporating it into several state-of-the-art methods, including AutoBoot and HIVT. The random mask pre-train has different strategies, point-wise, patch-wise, and time-based, each serving a distinct purpose. All cases show 75% blue masking in total, and remaining data in gray will be fed into the network as shown in an example in the left. The point-wise approach primarily facilitates the learning of interpolation and correlation over a short period of noisy data. In contrast, the patch-wise method fosters an understanding of interaction over extended period. Inspired by the masked autoencoder approach to video data, each agent's trajectory is divided into non-overlapping patches in space and time given a certain time frame. The size of these patches is chosen randomly, and the patches are masked randomly. The time-based strategy simulates scenarios where a sensor might fail suddenly, leading to missing all data at that random time step. Since the three tasks corresponding to three special cases of masking, they can be carried out by adapting the same network architecture accordingly. With the pre-trained encoder from random masking, let's go through the three fine-tuned tasks one by one. First, for motion prediction, given the history track, we predict the future. We evaluate motion and conditional prediction on two widely used datasets, Argoverse and NewScenes. Here we show the visualization of motion prediction using AutoBoot with random mask pre-train on Argoverse dataset. It shows that the predicted green trajectories are accurate and able to capture diverse modes. In new things, our approach achieved comparable results to other state-of-art methods. Compared to the baseline, the application of random mask shows marked improvement in the matrix, including mean ADE miss rate for the top 5 in 2 meters. In Argoverse, we incorporate two methods, AutoBoot and HIVT. Both of them show a positive impact on masked pretrain, resulting in a decreasing of ADE and FDE. In terms of conditional motion prediction, given the history information and the ego vehicle's desired future trajectory, it predicts all agents' possible future trajectory. We showed visualization here. Predicted trajectory of all other vehicles are shown in the dashed line. From the table, for both Argoverse and NewSync, it reduced the ADE and FDE. Given that Argoverse data features higher frequency and more waypoints, it is plausible that random mask exhibits superior performance as the input sets extend. To ensure fair comparison between pretrain and training from scratch, we highlight that we performed the experiment over comparable time period on the identical devices. Take an example from conditional motion prediction training for Argoverse. X-axis represents relative wall training time and Y-axis represents the ADE. The plot indicates that pre-train with fine-tune is more accurate than training from scratch. Meanwhile, it can learn other tasks from the same pre-trained task at a faster rate and a better result. Occlusion handling is a case of motion prediction where the input contains agents occluded over time. Question comes, how to find the data with occlusions? Since Argoverse and NewSync dataset are collected from the ego vehicle, they cannot really capture occlusions. We use multitask interaction dataset instead. This dataset is collected by drone and potential traffic cameras, which enables the potential to label occluded object from the perspective of a single vehicle. We auto-labeled occluded objects in the validation dataset based on a randomly designated ego agent. From a bird's-eye view and the given positions and size of all agents, we compute the occupancy grid. Objects within the occluded regions are labeled as occluded in dark blue. The network can only access the agent's waypoint annotated as visible. Therefore, for the agents that are partially occluded, the network can only see incomplete history. We then measure how the network can capture such partially occluded agents' future trajectory. As shown in table, the use of random mask enhances the network's capability to predict the partially occluded agent's future trajectory, with improvement exceeding 30% for both ADE and FDE. The results are not surprising, as the pretrain is a sort of random synthetic occlusion. Therefore, the pretrained network has a considerable advantage over a network simply trained with bird's-eye view data and no occlusions. As a conclusion, in this paper, we propose a simple and effective random mask pretrain framework, which facilitates the motion prediction task in general and a conditional motion prediction. Furthermore, this framework largely improves the prediction accuracy for occlusion scenario. The self-supervised learning and masked autoencoder can be further explored with state-of-the-art techniques in the field of motion prediction for autonomous driving. Thank you for your listening. Check out our paper and code if you are interested.